Welcome to This Explainer, where we're going to completely demystify the hardware, the physics, and the networking logic that makes low Earth orbit satellite internet magic actually happen. We rely on the digital world every single day, but we rarely stop to consider the staggering physical infrastructure that makes it all possible, especially when that infrastructure is literally streaking across the sky right above our heads. So today, we're breaking down the anatomy of networks like Starlink to see exactly how they work.
Here's our agenda for today. We'll start with the speed of light problem, then move on to the orbital swarm, lasers and space routing, ground and direct-to-cell tech, the journey of a data packet, and finally, space safety and the future.
Let's dive right into Section 1, the speed of light problem, the ultimate physical bottleneck. For decades, satellite internet was plagued by this massive, totally unavoidable delay. Historically, internet satellites sat 35,000 kilometers away in geostationary orbit. At that altitude, they match the Earth's rotation, so they appear fixed in the sky. But here's the catch. A data packet still has to travel 35,000 kilometers up and 35,000 kilometers all the way back down. Even traveling at the speed of light, that sheer physical distance creates a 600-plus millisecond latency. That's more than half a second, and it made real-time applications like a smooth video call for work or playing a fast-paced online game basically impossible. You were literally physically limited by the immense distance to space.
But Starlink completely solved this problem by drastically dropping the infrastructure down to a low Earth orbit of just 480 kilometers. By bringing it that close, the physical distance your data has to travel is reduced by a factor of 70. Because of that massive drop, latency is slashed down to a blistering 25 to 35 milliseconds. We're talking about an orbital network rivaling the responsiveness of your normal terrestrial broadband at home. It's a total game changer.
Moving right along to Section 2, the Orbital Constellation Swarm, synchronizing 9,000 satellites at 27,000 kilometers per hour.
Now, because these new satellites are so incredibly close to Earth, they don't just stay fixed in the sky. They are streaking across it at 27,000 kilometers per hour. That is faster than a speeding bullet, completing an entire orbit of the planet in just 90 minutes. So a single satellite is only visible to you for a few minutes at a time. To maintain constant, uninterrupted coverage, you need a massive, synchronized swarm of over 9,000 active satellites. And managing a swarm of that size requires constant optimization. For example, look at the recent reconfiguration that lowered thousands of satellites from 550 kilometers down to 480 kilometers. It perfectly illustrates a vital engineering balance. First off, being 70 kilometers closer improves radio frequency path loss, giving you a better, stronger signal. But equally important is space safety. As we approach a solar minimum around 2030, atmospheric density drops. At 550 kilometers, a dead satellite could just linger up there as space junk for over 4 years. But at 480 kilometers, the atmospheric drag guarantees that a failed satellite quickly burns up in the atmosphere in just a few months.
And the machines themselves, they are absolute marvels of propulsion and design. They aren't those bulky cylinder-shaped satellites you might be picturing. They're actually sleek, flat-panel designs that weigh anywhere from 227 kilograms up to 800 kilograms for the newer variants, which is roughly the weight of a grand piano. And remarkably, they don't use traditional chemical rockets. Instead, they maneuver using incredibly efficient Hall-effect ion thrusters fueled by Krypton or argon gas. These thrusters use a magnetic field to accelerate ions, providing the super-precise, low-thrust propulsion they need to maintain orbit and dodge collisions.
All right, Section 3, lasers and space routing, building an optical backbone in the vacuum of space. In older bent-pipe satellite systems, the satellite had to physically see both you and a ground station at the exact same time to give you internet. So if you were out in the middle of the Pacific Ocean, you were pretty much out of luck. The incredibly elegant solution to this is optical intersatellite links, or OISLs. This is a mesh routing system where, instead of relying on ground stations, satellites shoot highly focused lasers at each other straight across the vacuum of space. They are literally bouncing data from satellite to move it across entirely different continents.
And there's actually a massive physical advantage to routing data through a vacuum. Light travels 47% faster through the vacuum of space than it does through the glass of terrestrial fiber optic cables buried underground or under the ocean. Think about that for a second. Because of this enormous speed boost, an internet request jumping from a user in Mumbai to a server in London might actually arrive faster by beaming up and bouncing through this orbital laser mesh than it ever could traveling through physical undersea cables.
Section 4, ground tech and direct-to-cell, catching a signal moving at orbital speeds. Because these satellites are flying overhead at Mach 22, a traditional spinning dish with mechanical motors simply couldn't track them fast enough. Instead, users rely on phased array antennas. These are entirely flat panels with zero moving parts. They track satellites instantly by using hundreds of tiny antenna elements. By delaying the radio signals emitted by each element by just fractions of a millisecond, they create interference patterns that electronically steer the beam. It snaps to a new satellite rising over the horizon in microseconds, all without a single gear turning.
But it gets even crazier. One of the most exciting recent evolutions is the direct-to-cell architecture. This allows your standard, everyday, unmodified smartphone to connect directly to these space cell towers. But to pull this off, engineers had to solve the Doppler shift. Because the satellite is moving so incredibly fast relative to your phone, the radio frequencies literally compress as the satellite approaches and stretch as it flies away. It's exactly like how the pitch of a speeding ambulance siren changes as it drives past you. To make this connection work, custom silicon and advanced algorithms are aggressively pre-compensating for this massive Doppler shift in real time just to catch your phone's faint signal.
Section 5. Journey of a data packet. From your phone to space and back in milliseconds.
So let's put it all together. Imagine you just click a link on your phone. Here's exactly what happens. First, your phone sends the request to your Wi-Fi router, which passes it to the phased array terminal. Next, that terminal electronically steers a beam to the absolute optimal satellite overhead, uplinking your packet into orbit. Then, that satellite receives it, and if the destination is far away, it fires an optical laser to an adjacent satellite, routing your packet seamlessly through the space mesh. After that, a satellite directly over your destination downlinks the packet to a massive terrestrial gateway, dropping it straight into the global fiber backbone to hit the server. And finally, the server's response races right back to you following the exact reverse path. All of this insane choreography happens in less than 40 milliseconds.
Bringing us to our final section, Section 6. Space safety and the future. Starshield, orbital preservation, and what comes next.
This core architecture we've been talking about is naturally expanding beyond just consumer internet into platforms like SpaceX's Starshield, utilizing the exact same underlying low Earth orbit mesh and laser links, but outfitting them with high-assurance cryptographic hardware. It's explicitly designed for government and military applications. It hosts classified payloads and acts as this highly resilient, essentially impossible-to-sever digital nervous system for defense entities operating in orbit.
At the same time, managing all this orbital traffic is absolutely critical to prevent Kessler syndrome, which is a catastrophic chain reaction of space collisions. The swarms mitigate this by autonomously dodging debris. They actually use U.S. Department of Defense tracking data to detect potential conjunctions, and then automatically fire their ion thrusters to get out of the way. And, like we discussed earlier, by leveraging those sub-500-kilometer altitudes, operators guarantee that any unpowered or broken hardware is naturally pulled down by the atmosphere, incinerating completely cleanly and preserving the orbit for future generations.
Knowing the sheer physical scale, the ingenious engineering, and the blinding speed of what we've just unpacked today, it really leaves us asking a profound question. As this invisible, impossible-to-sever network continues to blanket the globe, how will it permanently reshape the boundaries of human connectivity and global security? I'll leave you to think about that. Thank you for joining me on this explainer, and keep looking up.